All right, thank you everyone for doing your homework today and watching this video. To define an acid, in grade 11, you learned that an acid is a proton donor. So if we look at hydrogen chloride and we put it into water, what's going to happen is we're going to produce hydronium. So the hydrogen from HCl has joined onto water and created something called hydronium. This also leaves us with chlorine on its own. So this is our acid. We're going to talk about why water is our base next. And here, this is our conjugate acid, and this is our conjugate base. Your conjugate base is everything left over from your acid, and this is what happens when you add a hydrogen to your base, conjugate acids. A base, on the other hand, is a proton acceptor. And if you're unsure of proton, we also use in chemistry hydrogen plus is a proton because it just has one proton and no neutrons. So the hydrogen is being donated, and that's why we call it the proton donor versus proton acceptor. So in the above example, we have water accepting the hydrogen from HCl and acting as a base. The reason why we changed to this definition rather than Arrhenius, which just said OH, is because we have something like ammonia. When we put it into water, water actually acts like an acid, donating a hydrogen onto ammonia. It will produce ammonium, which is NH4 plus, and we're left with hydroxide. So because ammonia accepted the hydrogen, it is the base. Since water donated the proton, it is the acid. Here, I have a conjugate acid and a conjugate base. Okay. Notice that we have two examples with water, and in one example, it's acting like a base and acting like an acid. So I want you guys to tell me what is the term for that tomorrow, and I'll know that you've watched this video if you know what that's called. Titration. So the definition of a titration is a lab technique to determine the concentration, this is a short form for concentration, of an unknown substance with a known substance. We're going to look at an example of this tomorrow. Okay, but you can watch Miss Nautical's videos if you want to review. I'll post them on the classroom with this video. So for pH and pOH, we're going to look at different calculations. Remember that pH measures the hydrogen ion concentration and pOH measures the hydroxide ion concentration. So in example 1, we're asking for the pH of a solution that contains 25 grams in 1.34 liters of water. So we have to do a couple of steps here. We know that eventually we want to get to the pH of answer for the pH. So we are going to have to use negative log hydrogen ion concentration. We're given here grams and liters, so we have to convert that into concentration. This is something that we've been working on a lot this week. So if we have a mass of 25 grams and we're looking for a concentration of HCl, we're going to take the 25 grams, divide it by 36.46 grams of HCl, that's our molar mass, grams per 1 mole, and we get 0.46 moles per liter. I can put that value right into my pH equation because I know that HCl is something called a strong acid. And until we get to chapter 8, we're only going to talk about strong acids and strong bases. That means that we're going to fully ionize into H and Cl negative when we are put into water. So because 100% of whatever my concentration is now my hydronium concentration, that means that this concentration is my hydronium ion concentration, even though it's talking about HCl. So I have negative log 0.46 moles per liter. When I put this into my calculator, I get 0.34. An important SIG-DIG rule for our pH that we're going to just make a note of, whatever your SIG-DIGs were here, so from this question I have 2 SIG-DIGs as my smallest, that's how many decimal places we need in our precision for our final answer. So that's why we had it here. It just works out that this is the same number, 2 SIG-DIGs, 2 decimal places. If I had 3 SIG-DIGs, I would have had to add another unit, and that would be 3 SIG-DIGs, 3 decimal places. Yes, did I lose you here? We can talk about more tomorrow. I'll include it in the lesson. All right, you can pause if you wanted to go back and rewind there. We're going to do question number 2. So question number 2 says, what is the pH of a solution containing 1.0 times 10 to the negative 2 moles per liter of sodium hydroxide? So since I'm working with sodium hydroxide, which again is strong, it's a strong base, I know it will fully dissociate, ionic compounds dissociate, into sodium hydroxide, so the ions. I want to look at the pH of a solution. I know that I have 1.0 times 10 to the negative 2 moles per liter of sodium hydroxide. I'm going to have the same concentration of my hydroxide ion. Since that is the case, I can calculate my pOH because again, it's measuring the concentration of hydroxide. When I put in my value here into this equation here, the number that I get is 2.0. And again, I have 2 SIG-DIGs here, so I need to have 2 decimal places in my final answer, so I have to write 2.00. Now, I am solving for my pH. I know that pH plus pOH is equal to 14 based on our equations from last year. So I need to find pH. I'm going to say pH is equal to 14 minus pOH. 14 is an infinite number. So my final answer will be 12.00. Okay, so this one should change for SIG-DIGs. So the 14 does not affect the fact that my precision is 2 decimal places. That's all for homework tonight. I'm just going to put on the sides all of our important formulas. If you're going to do more review, pOH. Keep working hard, and we will touch base again tomorrow. We also have this formula here and this one here. Thanks for watching.